In this video, we'll look at continuous distributions of charge, where the charge is distributed uniformly as opposed to discrete point charges. We'll use the concept of charge density, and we'll still use the concept of superposition of point charges, but we'll need to use integration instead of summation. So charge density is defined based on charge. So we use a symbol Q for charge. It has a unit of Coulomb. For linear charge density, charge distributed uniformly along a line, we'll use a symbol lambda, and that will have a unit of Coulomb per meter. For surface charge density, we use sigma, Coulomb per meter squared for that area, and for volume charge density, we'll use rho, Coulomb per meter cubed. So if we look at an example of charge density over a line, different types of surfaces, and over a volume, if we look at a charge of negative 300 elementary charges, so in excess of 300 electrons, distributed uniformly along an arc of charge, where the arc subtends an angle of 40 degrees with a radius of 0.04 meters or 4 centimeters. We want to know what is the linear charge density. Well, we can use our theory. Linear charge density is charge per unit length. The length we need here is arc length. So our arc length formula, r theta, where theta needs to be in radians. Our SI unit for angle is radians. We have pi radians is equal to 180 degrees. And if we want our answer in coulombs per meter, we need to change elementary charges to coulombs. And we can then just plug and play. Lambda is charge per unit length. Our charge, negative 300 elementary charges. Our length, our theta. And plugging in for elementary charge, changing from degrees to radians, we come up with, we have negative 1.7 to 2 significant digits times 10 to the negative 15 Coulomb per meter distributed along this line. The charge itself is on the order of 4.8 or 5 times 10 to the negative 17 coulombs, but the charge density is going to be higher than that, 10 to the negative 15 coulombs, because of the short length of the wire. The length of the line is only less than 3 centimeters. So that's an example of linear charge density. If we look at an example of surface charge density, where we have the same excess of 300 electrons uniformly distributed over the face of this circular disk only has a radius of 2 centimeters or 0.02 meters. We want to know what is the surface charge density, sigma, in Coulomb per meter squared. So that theory, sigma, surface charge density, charge per unit area. The area of this circular surface is pi r squared, and the elementary charge is still 1.602 times 10 to the negative 19 coulombs. And then we find our solution by plugging in our numbers correctly, and we end up with a surface charge density of negative 3.8 times 10 to the negative 14 Coulomb per meter squared. And we should also, always do a check. Does this number make sense? When we have a charge on the order of 3 times 1.6, or approximately 5 times 10 to the negative 17 coulombs, our charge density is much higher, charge per unit charge per meter squared. But remember, the radius here is only 0.02 meters, so it's only 2 centimeters, so we increase that charge density number as opposed to the total charge. So that makes sense. Well, what other types of surfaces do we use? Symmetry is often used in physics to make problems solvable by hand as opposed to by a computer. The other highly symmetric geometry here is a sphere. So if we have a uniform charge distributed uniformly on the surface of this sphere, same 300 excess electrons, our radius here is still 2 centimeters or 0.02 meters. We want to know what is that surface charge density, Coulomb per meter squared. We still use surface charge density as charge per unit area, but our area of surface area of the sphere, 4 pi r squared. So we can plug in and get our solution. Once again, we have, we have negative charge, so we have negative surface charge density on the order of 10 to the negative 15, 9 times 10 to the negative 15, so it's close to 10 to the negative 14 coulomb, still unit of coulomb per meter squared. Lastly, let's just look at the same sphere, but instead of a uniformly distributed charge on the surface, that charge is uniformly distributed throughout the volume. So we will look for rho, our charge per meter cubed, is the theory there. So we'll look at charge per unit volume, the volume of a sphere, 4/3 pi r cubed. And we find when we plug in our numbers properly, we end up with a volume charge density, which has a charge density which is a much higher number than the charge itself. Again, the radius of this sphere is only 2 centimeters, and we're looking at coulomb per meter cubed. So our number check, in fact, makes sense. So let's look at an example of electric field due to a line of charge, and we'll use linear charge density. And again, this example can be related to current in a wire. So it's an appropriate example. It has symmetry. In this case, we'll look at charge on a uniform ring. So charge going around in a circle. For example, if we're looking at current in a wire. So this uniform ring of charge has a radius of r in meters. We know its charge density lambda in coulombs per meter. And note here it says it's a uniform charge density. That's important. And our total charge then will be that charge density times the length. Well, the length of this entire circumference is 2 pi r. So our strategy here is we'll look at this infinitesimally small element on this linear charge density. So this infinitesimally small element of charge we can consider a point charge. In this case, it's largely exaggerated. So we'll treat this little length here as ds and that little charge as dq. So just like q is equal to lambda times the length, our dq is equal to lambda by our differential length, or lambda ds. So we'll use that differential charge element to find our differential electric field. So the electric field due to this little differential charge element will be along this line to point P. Note that point P is at the central bisector here, or along the axis of the center of this ring. So we are using symmetry in this problem to make it easier to solve. So from our differential charge here, ds, looking at it like a point charge, we go along the line. The electric field will assume the charge is positive, then the electric field will point away in this direction. Well, that's differential electric field due to the differential charge dq. That dq we can define as lambda ds. Well, what's that distance r? Our distance r we can find using Pythagorean theorem is the square root of our z squared plus r squared, and that gives us the magnitude of this little differential electric field element. Well, that's just one differential electric field element. What if we looked at another little differential electric field element 180 degrees away from, we'll look at differential charge 180 degrees away from our original differential charge. So in this case, our electric field will still point away along this line. It will point upward. If we wanted to sum up these two, well, we have to sum up the vectors, right? So we sum up the vectors. We can again use this concept of symmetry here. If these are 180 degrees apart, if we define this axis as being our r-axis, where theta then is equal to 0, phi is equal to 0 if we do our r phi z axis, and our differential electric field due to 1 will be that magnitude of electric field cosine of this theta angle here in the k direction plus sine of that in the r direction, and we'll say we're at 0 phi. Our differential electric field due to 2 is going to have the same angle of theta. Since we're 180 degrees away, this angle is also going to be the same theta. So we have the same magnitude electric field, cosine theta in the k direction, but our the sine theta component is going to be in the negative r direction. So these, when we sum them up, these two are going to cancel. Those are 0 anyway. And we can sum up these two, and we just get 2 times our magnitude of the electric field times the cosine of theta. Well, what if we were to try to sum up all of these differential elements around the entire circle? We can see that if we could pick a point here and a point here, and they're always going to cancel in their radial and phi components. Only the z and the z components are going to sum, and they're all going to sum upward. So how do we sum them all up? We could do it discretely, but it's easier to use our calculus and integrate and do it continuously. So our electric field E is equal to the integral of all the dE components around our circumference from our equal to 0 to 2 pi r. Our plugging in for dE, the magnitude of dE, our cosine theta in the k direction. Cosine theta then, this angle theta is the same as this angle theta. The cosine of that is z over little r, or z over square root of z squared plus r squared. We can pull everything out except for our ds. We're still pointing in the k direction. These k's are different here. This is our unit vector in the z direction, 1 in the z direction. This is our electrostatic constant k. When we do our integration, then we multiply by 2 pi r. Well, lambda 2 pi r is in fact the total charge, so we get our electric field is equal to our electrostatic constant, z over z squared plus r squared to the 3/2 times our charge q in the k direction. So if we try to summarize here, we found the electric charge the electric field due to a charged ring along the central bisector of the ring axis. And we did this without any assumptions, so this is the exact equation for that, exact formula for this situation. If we try to understand this, we'll look at points very far away from the ring. Points very far away from the ring, our distance z is going to be much greater than the radius of the ring, and in that case we can assume down here this is just going to be our z squared plus 0, and we end up with z over z cubed, or our electric field is equal to kq over z squared. It looks just like a point charge. If we look at a point right at the center of the ring, then our z is equal to 0, so our electric field is equal to 0, which makes sense since all our electric fields, we said our shell theorem tells us that inside a charged shell of charge, our electric field is equal to 0. Similarly for inside a ring of charge. If our charge happens to be negative, then our charge density will be negative, and our electric field will point down instead of up. If our charge is positive, the electric field will point up. So in future videos, we'll look at examples of surface charge density to set up integration and solve continuous distribution of charge to solve for electric fields.